So our talk today is going to be coming from the trenches of trying to use all these tools in a architecture firm. So our title's Form Jamming with AI Agents. Briefly, form jamming is trying to make sense using these AI tools on projects. I mean, earlier this summer, we came up with this term form jamming as a way to think about these AI tools in combination with each other. I mean, we've been experimenting with these tools, as we all have for the last couple of years, AI coding and cursor and image generation. We felt like earlier this summer was the tipping point where the models have gotten better, the AI coding tools have gotten better, and it felt like we can use these in production on our projects, and we'll be talking more about that in a second. But Junling and I are from HDR. We're a large architecture engineering firm. We have a computational design group at HDR, about 15 people. We're split between software developers, computational designers, a couple of people that focus on AI. We have a couple data scientists that make our group a little bit more unique than different firms out there. So again, we build tools, we work on projects, we develop services. HDR overall, we're quite large, and so we support mainly our architecture group, but we certainly work on transportation, water projects, all kinds of stuff. So a couple parts to kind of introduction to this concept of form jamming. And this is where, earlier this summer, when we started thinking about trying to make sense of these tools coming together and actually working on projects, the things that we were thinking about, on one side of this, tools in architecture take a long time to produce. So along the top here are algorithms. So you have the Pierre-Bézier curve from 1958, and it didn't get implemented into AutoCAD until around 1980. CATIA in 1977. And then, as all technologies do, they get implemented in automotive film faster than they do in architecture. And so the FOA building, even though it's not documented as using Bézier curves or AutoCAD, it seems to be one of the most clear examples of a large project implementing this algorithm and these tools. It wasn't until after this that we had Bilbao, larger Zaha projects. And so just seeing that pace of, the algorithm, 20 years to AutoCAD, 20 years to getting fully implemented on a project. The most clear-cut case of this that I think everyone's probably familiar with is, Bilbao, Frank Gehry, and using CATIA to do that project. So the project before Bilbao was the Vitra building, and it was famous for having a kink in the building, and from there, Frank Gehry started using CATIA, which eventually turned into digital projects. But this is a very specific use case of these kinds of tools because it was about his models and the tools achieving exactly what he wanted to do from a design perspective. So this is in direct contrast to what comes a little bit later. And an example I really like is the Grey Glen embryological house project. Now this was there's kind of a genre of this work that happening from Grey Glen and then many others afterwards, but his thesis on this was around mass customization and using the algorithms and coming from animation, so it was about using alias, and it's actually quite simple. All he's doing is taking the Bézier curve, modifying the points, and then using the animation software to interpolate between the options. Now, at the time, this was, nobody in architecture was really using animation software. I actually like the road. The image up there is like the first Lucas rendering. Which I'm actually fascinated by as a sidebar, because people saw that first rendering and thought, this was like, we should use this to make films. And now, now it's like you show somebody an AI image with one artifact in it, and they're like, oh, it'll never work. But this concept of like the tool and the output of that becoming the work and having a framework around that that Greg did in the embryological house is something we've been thinking a lot about. So that's one part of the conversation around form jamming. The other, and that's about tools taking a long time to be implemented in architecture. The other, I really enjoy kind of tracking VFX animation tools, especially as it relates to architecture. It's just all how it crosses over. Maybe one place to start on this is the Wild Robot 2024 film. I think this is a perfect use case of using AI tools, even though these film studios don't talk about this much, which I think is something that we in architecture deal the same way. But it's mainly because they use so many tools that it's never about just using one single tool. And 2026, this Critters movie that's coming out, this backed by OpenAI. Personally, it's a cool project because it's using AI, but it's a bit deceiving because the whole point of it is they're trying to make films for a fraction of the price. That is a direct comparison to the way they made Toy Story with John Lasseter and Ed Catmull and Steve Jobs. John Lasseter, when he pitched Tin Toy to Disney, everyone at Disney got excited because the head of Disney said, okay, well, you can do it, but you have to do it for half the budget. And then he said he wouldn't do it, and then that's how he left Disney and then met Steve Jobs and ended up building Toy Story. So I always think, like, as new technologies come out, speed is one component of it, but saying that you're going to do it for less money is always a bad route to go. But all these, I always think that these tools in VFX become interesting as it relates to architecture and form jamming, because then it's just a matter of like using all these tools on projects. So one project we've been doing this summer, we call it Block 99. This is work. This is a work that it's an interactive installation and web app that we installed at the Kaneko Museum in Omaha, Nebraska. So it's part, using AI coding for the web app parts, for image generation, for building the hardware. It kind of encompasses all these ideas of just like trying to make this stuff happen on a project at like all means possible and as fast as possible. We did this whole project in 2 weeks. So we bought this TI 99 computer, actually got it working straight out of the box. Played the Pac-Man Munchman game. Took apart the keyboard and rewired it to get it working. And so we had this whole idea around using retro hardware to design the thing. And we rebuilt it to add knobs and sliders. So this is all about like just, if we can move at this rapid pace of building our own tools, why not build physical devices as well with this? So this is what the final result looks like. So on the right, we cut out part of the computer where the old video games go, and we added buttons and sliders that you interact with it. So it's kind of like a Lego building component, and it's actually quite simple because it wasn't necessarily about the algorithm, even though we had ideas of going much further with this. It was just simply about, it's almost like building your own modeling application, simple block building, and then using the computer as a way of like interacting with that. And so the output of this, we have all these little physical model aesthetic out of it. We kind of see image generation as almost like a rendering engine. We have our own, it almost kind of seems trivial to talk about image generation at this point, but I'd say, in-house at an architecture firm, when you're trying to build, you're trying to fine-tune an image model to be in production, does take a fair amount of work because it's got to sit in-house. You got to fine-tune it. You want to make it be aesthetically pleasing. So all that work was great. We did that this summer in 2 weeks. And but you know, the other part of form jamming, so that's like a single project that's output into a museum. The other part of form jamming is just trying to work with these agents in a quick way. And so Junling's going to talk a little bit how we've built our Rhino MCP, kind of the technical framework of that, and how that's kind of fitting into our pipeline.
Hi.
Here.
Hi. So when we saw the NCP, which is the model content protocol, we are really excited, especially when we saw the Blender NCP, which show us a lot of like potential for 3D modeling agent, and we immediately put it into our radar and start to develop our own Rhino NCP. So, but there is a couple of the challenges we made in our development process. Firstly, we developed a local version Rhino NCP, like Blender NCP, to run locally in the user's laptop. But we finally end up with like finding it's really hard to do the team cooperation, and when we want to update the feature of this Rhino NCP, and the user need to reconfigure it. So we think about develop a cloud-first architecture. So we are maintaining a centralized Rhino NCP manager in a cloud that every single user will have their own Rhino NCP user instance and their ports that associate with the memory and also the geometry data for their own Rhino NCP. This one actually make us like more easily, when we update a new feature, the user can have these new features mostly updated in their laptop. So here we have a lightweight Rhino plugin that you can run the Rhino plugin in the Rhino. Then we can register in our web application part and copy paste this information, credential, and get your Rhino own NCP with some, so here is the example of the interface. So you can use this NCP instance to connect with any NCP client, such as our desktop, the cursor. So another thing, actually this architecture introduced another challenge for us. How can a remote NCP server control local user Rhino? So we actually designed a 3-layer communication ports. So firstly, in the NCP client side, these will be communicate with the remote server with a streamable HTTP protocol. So then the remote server will send the request with the HTTP post with a SDK session and JSON to our lightweight Rhino plugin. So in this architecture, the remote Rhino NCP, every single user will have their own NCP server that can control and interact with the local Rhino smoothly. When it comes to natural language, we all know, natural language is quite limited when we want to use natural language to describe a 3D thing. So another thing we made is how we make the NCP server or the agent easily understand the 3D geometry data in the Rhino. So for example, the user say, I want to add 2 double glazed windows on the select walls. So we actually design a tool in the Rhino NCP, like every time the NCP server generates the geometry, to automatically generate the object metadata, such as like windows, for example, you will have the description, you will have the type, double glaze, and white, and you value, and then which is most important, the floor, which the Windows belongs to. Actually, this give the NCP server or the agent a more comprehensive, like semantic content. So these actually help benefit by this architecture. This actually help the agent or NCP to understand like which object they need to modify and which one they want to change. For example, in this case, users say change the material of the window at the second floor. So actually, we have an automatically filtering tool that can search in the Rhino scene to find out the qualifying object. For example, we input the window and the window at the second floor. Actually, we can return all information like qualified windows then back to the NCP server that it can do the next step. And also, another challenge for us is how we think about like make the agent or NCP to understand like more users, like more comprehensive intention. So for example, when users say, I want to make a previously like room earlier larger, but how the agent understand which room the user refers to. And we all know in the traditional NCP client side, for example, the cloud desktop, the cursor, they have great like agent memory in the user's like conversation prompting, but they don't really, if we develop the Rhino NCP, they don't really know what happened in the Rhino side. Even you can return a operation geometry response from Rhino, but it's not enough. So we designed a 3-layer memory system. Like every user will have their own instance, and the memory and operation will store in their instance, like in the remote server. So in the memory, it will include the user prompt, like also the agent response, and also include a lot of like operation IDs. This operation ID will record like the operation type in the Rhino and also which object they operate. So this actually give the NCP or AI agent a more comprehensive background, like what geometry, and make the geometry history operation more traceable. And here's an example, like in a single user, like you can how we store this data in our remote server. And another thing, like if you play with like Blender NCP or Rhino NCP before, one important tool is extrude code, which can bring it in infinity like possibility to your Rhino or Blender to do the 3D modeling. For example, anything you want, but we actually in our practice to developing this tool and using in our practice, we found really important challenge is that this tool take a lot of like errors when we because the Rhino syntax is not very popular in the internet, which means the agent doesn't have a lot of like prior knowledge about it. So we are building a small rack system. We get the documentation from the official website of the Rhino syntax, and we use the Crowd4 AI to get the data to the JSON file, different kind of JSON file. This JSON file will include the method of every single, the information of the every single method, include the categories, the method, and we chunk it into every single method into our Chroma Wiki database. So every time before the NCP server extrude the Rhino tools, it will look up the syntax, make everything more easy, make the response more correctly. And we also integrate other, for example, our internal material database to generate the material in the Rhino, and we develop a SQLite NCP server to connect with the Rhino NCP server. We also integrate our AI rendering endpoint to wrap that is a tool of part of the NCP server. So I will pass to the.
Yeah, just to wrap up in just a minute here. So a couple examples, in production, I think early on, using the MCP server, playing around with different agent algorithms, very early on, we were doing very basic stuff. This was before a lot of the Sonnet 3.5 model was out, so it was a lot more difficult. But I think what we found from these experiments is just simply like the like multi-step prompting is extremely important, and referencing databases is extremely important, which was what Junling was talking about with the RAG system. So in production now, we're building our own databases. So this is for a curtain wall system. So building a database of products and sizes that then the MCP can just reference that and build the curtain wall and options with that. So this is just like our goal of getting this into production and what that takes. And just finally, as a final slide, the MCP stuff, as it relates to form jamming, these systems aren't perfect, and that's exactly what we were describing with the first couple slides. And that imperfection of how the tool is operating and what we're doing with it kind of reminds me of when 3ds Max and Maya, came out in early 2000s, and the form was generated by applying modifiers, and that as a framework and a way of thinking about these AI agents, and not necessarily being, this perfect pipeline, this perfect set of tools, but being the framework that we're constantly iterating, and we're building all kinds of crazy tools for each individual project. So that's it. Thank you very much.
Thank you so much. Thank you very much.